my camera's here. Basically what you do is you hook up the battery and then you turn it on and then it waits. It should wait.
You didn't put in the battery.
Turn the battery on and then it waits and then you put it over, because it follows it stays on the black tape. So you put it over white and then you push a button and then you put it over the black tape. You push another button and that calibrates it for what the actual white and black values are for the room and for the whatever, and then you hit the button and then it goes. And it stays on the black tape by correcting itself and stopping the motors and turning.
And ideally it goes the whole time?
Ideally. Sharp turns are a little difficult because the sensors are close together. So, yeah. It just goes around this little loop that we made about 10 minutes ago.
We
have dials right here for the flat plane, and this is for our vertical. And then we have this awesome button that shoots a laser pen.
Go for it.
Yeah. It's pretty sensitive, and you're not going to hit any because it's. So we have a laser pen, which is very small in diameter, and then we have these photo sensors that are also equally small. Oh, nice.
You're trained to operate a UAV.
There you go.
Look at his concentration on his face.
I shot it.
Okay, so this is a quarter counter. We basically did it using an inductive sensor that sits on the bottom of this, then an actuator that'll kick out coins, kicks them out one at a time based on a clearance.
We have an LED display screen.
Yeah, so every time it kicks one out, it knows you have one. Really slow.
But you know, slow and steady wins the coin counter race.
Okay, and that was our last quarter.
How much do we have, Daniel?
$2.
Oh my goodness, they're worse.
So we don't really have like flow actuator valves, so we just kind of squish it in a rubber tube to control the flow. So you get a little bit of leakage just because these are little RC servo motors pinching on the rubber tube. So you select your setting. You've got the different settings over here, and then it's differentiated up here. And then you've got a fancy little button. So we're going to show the last one. It's called the trash can for a reason. So when you turn this dial, it's got 8 adjustable settings. You can program it yourself in the code. You push the button, all of them open, and it dumps a concoction of happiness.
So we did a color counting gumball sorter, kind of. So yeah, for all of you who want to sort your gumballs at home, we made this for you. So the way it works is we have a photo sensor at the end. It measures the frequency based on the color of the gumball. That writes to our chip. And so we have an actuator that has 0.3 kilograms of force, is that right?
Yeah.
And so we have a button that you can flip through. And so now it's red, which is our first LED. White again, fourth LED. Blue, which is our second. But yeah, it reads really quickly and I think
that's it.
Okay, so what we did was we made an LED arcade game. So as you can see here, we have 30 LEDs, and basically they just toggle back and forth. And you use the internal buttons, so you press button 1 to start, and then button 2, you want to hit it in the sweet spot, which is the red zone. And every time you press the button, the red zone, the toggling gets faster and faster. So you can see it's starting to get faster. And, oh shit. And then it outputs your score.
It's a constant that the program changes the duty cycle on a PWM 10 times faster than the fastest frequency to mimic the sine wave. It works. It has photoresistors on the top, and then when you break the laser beams that are shining on them, it plays the note. So we have middle C through middle A. So. And if you block multiple beams, it plays the chord. So it sounds kind of awful because we don't have much spread in our gums, but it works.
That sounds good.
You can get really bad noise if you block them all at the same time.
Do it. Do it, do it, do it, do it.
They're all blocked. There we go.
It's beautiful.
Okay, and now we're gonna play Mary Had a Little Lamb.
The idea was like a gauge cluster if you had an engine dyno, so you could monitor some vitals. So we have the main case is a TAC. Within the TAC we have water, coolant temperature, oil pressure gauge, and a pyrometer for exhaust gas if you had like a turbo car. And then we also have a LED shift light. So you can set it, user set down here off a potentiometer.
So the way we did it, we used a Hall effect sensor to measure the shaft speed of this gear. So every time this sensor gets close to a ferrous metal object, it triggers an interrupt in the code.
Diaphragm pressure transducer for the oil pressure gauge.
Courtesy of Ford.
So we didn't have a really great way to calibrate this. So basically, if you heat this with a torch until it turns cherry red, that's about 1500 degrees. So we can
And once the water temperature reaches 180, which is preset in the code, the external fan will turn on to
So our group made an electronic Etch-a-Sketch. So it holds a whiteboard marker. It can also hold a pencil if you're drawing on regular paper. Holds it in place. And then you control it with the knobs. It goes until the position you set it on the knobs, which are just pots. So you can set it to go longer without actually turning it the whole time. We built the motors and the frame out of scanner parts and stepper motors. And yeah.
Nice. Okay, so this is Rasp. This is the robotically assisted southpaw. The reason for that is because Jeremy has created the left hand to my right hand.
It is a replacement for a clumsy left hand. Control your left with your right. So the basic construction on this, acrylic frame, servo motors, fishing line running to the tips of the fingers here. We have some nitinol wire in the back that's a super elastic memory alloy, so it doesn't hold shape once it bends. Fingers move. It reads the potentiometer that then goes to the pot and says how to bend the finger.
Okay, so here we want to zero it out. This is so pretty much anybody could put this glove on, close their hand, and this would be considered the maximum point that the fist would close. So then we push a button on here and the fist will make a full displacement. And then now I can play with it. 1, 2, 3, 4, 5.
So the glove is kind of constricting on finger placement right now, but
There we go. It's microphone. I don't know, so there you go. Woo!